Pressure pushing down. Oh, no, okay, here we go, number 10. So now we're going to talk about pressure. So pressure is something similar to force. Pressure is related. Ooh, what's going on there? Is related to force, but it's not the same thing. And the relationship that we find between pressure and force is given by the following equation. Pressure is force over an area. And just as a reminder, force is given in newtons. Area, in this case, will be given in square meters. And pressure will be given in pascals. So that's PA. A pascal is actually pretty tiny, so if you think about it, it's 1 Newton per 1 square meter. An apple weighs about 1 Newton. A square meter is a little more than 3 by 3, so that's not a lot of force on one area. So I want you guys right now to try out another estimating problem, and I want you to estimate the pressure on your feet. So what is the pressure on your feet when you are standing? So we're not all going to end up with the same answers on this one, but I want you to try it out, pause the video, think about it for a few minutes, write out what you get. If you get all the way to the end, good. If not, come back to the video, go through my work as far as you need so that you can keep up, and then we'll see how you guys do. Okay, so what we basically got here is that I estimated my foot is about 10 centimeters wide, 30 centimeters long. Again, this is just a rough estimate. It doesn't have to be exact. Considering we're using 10 for gravity too, it's okay if you just use some round numbers. So I've got a 10 by 30 centimeter foot, and I've got 2 of them. So I'm going to spread my force over both of those areas. Remember, area is just length times width, and I want to get my units into square meters so that I can use pascals. So what I'll do here is I'll convert. Remember, there's 100 centimeters in a meter, so I'll divide it by 100. That's moving the decimal point over twice. So I have 0.1 meters times 0.3 meters. And when I plug that in, I get 0.03 square meters. And I've got 2 feet. So that's 0.06 square meters. Next thing I'm going to do is find out my weight. So my weight is approximately 145 pounds. And there's about 2.2 pounds per 1 kilogram. Remember, newtons is kilogram meters per second squared, so we need to have our units in kilograms here. So I'll just take that 145, I'll divide it by 2.2, and I get them about 66 kilograms. I'll just round up there. So I come down here, plug it into the force equation, and just multiply by 10, and I get 660 kilogram meters per second squared, or newtons. Now that I've got that, I can just come up here over and plug in for my pressure. My force is 660 newtons, and my area is 0.06 square meters. And when I plug that in, 660 divided by 0.06, I get approximately 1.1 times 10 to the 4th pascals, which is about the same. Well, that is 11,000. Yeah, 11,000 pascals. When we get into the part about atmospheric pressures, you're going to realize there's a lot of air pushing down on us. So on this one, we have a cylinder, and this is just going to demonstrate a principle here. Let's say this cylinder is filled with water, and we just have a generic point. So this generic point of water should have an equal force in every direction at a given depth. It'll all have the same force on it. These arrows are trying to kind of show going into the page, coming out of the page. It's hard to do on 2D. But think of it this way. If I put an object in water, and I let it sit there, and it had a different force on it from a different direction, it would move. There'd be a net force on it. So basically what it's saying is there is a net force of 0 on objects that are underwater as long as they're not moving. So a point will have the same pressure on it from all directions at a given depth. All right, number 13. I want you guys to think about this. Consider the following on if I've got a diver underwater, and it's a super deep lake, 50 meters deep here, 100 meters deep here. I've got a scuba diver. I've got another scuba diver. Let me put a little scuba gear on, give him a little scuba. There we go. Scuba tank. Oh, I forgot his goggles. Gotta have the goggles. There we go. There we go. I want you to think about this for a second. Will the pressure be different? And if it is different, where is it going to be greater? So just take a second, pause, think about it. Did you pause? Are you lying to me right now? All right. You probably guessed it's going to be greater on the guy that's at the bottom. But you can think about it this way. Which one of them has more water that's being attracted by gravity down onto them? The guy that's down at the bottom, he's got 100 meters of water above him, which is going to push more down as gravity pulls on it. The guy with 50 meters has less. If you ever swam in a pool before, you've probably noticed this. The further you go down, the more you start to feel your ears push in. Those of you who have not the best ear tracks have probably gotten water in your ear the deeper you've gone. So as we can see, the more stuff that's above you, the more pressure you're going to feel from it pushing down on you. But the relationship we find is that for a given or for any fluid, the deeper you go in it, the more pressure you're going to feel at the bottom. Mathematically, we can see this relationship by looking at our pressure formula. Pressure is equal to force over area. So this is just the force of the water on our diver. His area doesn't change as he goes down, so that shouldn't affect it at all. But now what we're going to look at is how do we find the force of the water? Well, it's just the gravitational pull down on it. So we just get m of our water times the force of gravity, and that's still over the area of our diver. We know with a fluid from our density formula that we had earlier that we have rho times volume. So the density of water times the volume of water times gravity over the area of our diver is going to give us the pressure on him. But now we can think about this in terms of like spatial dimensions. The depth of water times the area of the diver is going to be the amount of pressure that's coming down on him. So remember, this is the pressure from above. So if we look at this, we get density times the height of the water times the area of our diver, because there's just a column of water above the diver that's pushing down on him, times gravity, and that's over the area of our diver. So we can cancel that out, and what we find is that the pressure of a fluid is the only variable here, because pressure should not change because water's not compressible. Or sorry, density shouldn't change because water's not compressible. Gravity's not changing significantly. He's only going a couple meters. So the only thing that's changing is the height of the water. So pressure in a fluid is related to the density of the fluid, the height of the fluid above you, or the depth, times the acceleration due to gravity. And in this case, the only thing that's going to be changing for our problems here is just the height. So pressure is just directly related to the height. So based on this, I want you guys to try and rank the following points in this tube. Tell me how much, or the order of how much pressure they should have. So I want you to rank them for me from least pressure to greatest. So least to greatest pressure. And I'll give you 5 points that are in this tube. Here we go. We have A, We'll call this guy down here B. This guy up here C. Then we'll have D over there. And then we will have E right there. So I want you to go ahead and pause the video, think about it real quick, write them down, and come up with your order. Did you pause? Are you lying? Okay, here we go. In this case, the one with the least pressure are going to be the ones closest to the surface. Does it matter that C is not exposed to air? No, because it's still the same amount of depth. I tried to keep it level, at least for your viewing. So in this case, A is going to be equal to C is going to be equal to E, and they all have the least. B is the next deepest, so those are going to be less than B. And then D should have the greatest pressure because it's at the greatest depth. One last thing to say about this is that pressure is independent of shape. So pressure independent of shape. Meaning if I had some like weird shaped vases full of water, let's say I had one that's just a square, one that's like a triangle. There we go. We could even have one shaped like a star. Look at that, that's pretty cool, right? And then maybe like one circular one. And they're all filled with water at the same height. And then I put a point at the same depth in each of them. It doesn't matter what the shape of the water is above them. There's still the same column of water that's above them. It only cares about depth. So these would all have the exact same if I was good at drawing their depth the same. But in this, depths are all the same, pressures are all the same, doesn't matter the shape. So let's try out a problem with this. Let's say that I've got a water tower. And there's an interesting thing I can tell you, a little story I can tell you guys about this in a second, where I got to learn it firsthand. Let's say we got a water tower here, and we got water in it, and it's filled to a depth of 30 meters. I want to know, what is the pressure? So what is P? Let's say there's a little tap here. It's down, there we go, 30 meters to the tap. Here's our little spigot. Water is going to come pouring out. I want to know, what is P at the tap? So go ahead, try it out based on the formula that you guys just got, and I will be back with you in just a second to show you the answer. All right, so we mentioned that this was a water tower, so obviously our rho is going to be 1,000 kilograms per cubic meter. Gravity is always 10 meters per second squared, and the height of our water tower above the tap is 30 meters. All I'm going to do is multiply through, and I get about 300,000, or 3 times 10 to the 5th pascals. Cool beans. All right, let's try another one. In this one, we're looking at the Hoover Dam that is in Westerville. So the Hoover Dam holds back water, which is on average 20 meters deep. All right, let's say, the lake that it holds back, the reservoir, is 13 kilometers long. If the dam is extended an additional 1 kilometer away, how much thicker? So in this case, I'm just looking for like a multiple. How much thicker should the dam be? And you can do this just based off pressure. So go ahead, pause it, think about it. Don't just let me answer it, otherwise your brain's not going to grow. You learn more from being wrong than you learn from not trying at all. Ha! Tricked you! Let's look at the pressure formula. Pressure equals rho G H One thing you may think, oh, there's way more water, I've got to hold back. Well, no, the ground is holding that water up. All that matters is the pressure from the depth of the water. Density of water doesn't change. Gravity doesn't change. Height of the water does change. No, doesn't change. We're just extending it backwards. So if you look at the dam, that would be like me drawing this picture here. Here's my dam wall. Watch your language, Mr. Gillum. I know. And here's the old edge of it, and all they do is just go like this and just extend it a little further that way. Depth does not change. Pressure on the wall doesn't change. Don't need to multiply the width of the wall at all.